Welcome back everyone to this series on machine learning applied to a real-time strategy game. This is still Arno, and in this video we're finally going to do some actual reinforcement learning. You now have all the context you need to understand what the big plan is here, so let's get our hands dirty. Reinforcement learning is like training your dog. He does something good, he gets a reward. He does something bad, he gets a punishment. Or let's call it a negative reward. But certain behaviors are not at all times good or at all times bad. For example, you don't want your dog to relieve himself indoors, but it's okay if you're out on a stroll together. It's really situational. So if we translate all of this to reinforcement learning applied to our favorite tank of all time, Tankdrick, we get the following. Tankdrick perceives the world and does whatever a Tankdrick does. His actions, given a certain situation, have consequences, and for this he gets rewarded or punished. That's all nice and theoretical, I know, but we still have to actually implement all of this, and that is what this video will be about. For this, we will need Unity with the ML Agents plugin and a Python 3.6 environment with TensorFlow and preferably also TensorBoard. It's also great if you can hook up a good graphics processing unit or GPU, better known as just your computer graphics card. Unity is then going to function as the environment, and Python TensorFlow is going to do all the learning. Not going to explain the installation here, there are plenty of great tutorials on installation out there. Mine wouldn't add much value, I believe. Instead, we're going to do a very naive and optimistic attempt here. We will need to define 4 things. First one, sensory input. How does our little Tankdrick see the world? Second is model output, so what actions can it perform? Then the third one is its brain settings. We get to determine a few settings on how the algorithm is to train. For example, how much information can it store, how much information it should consider at any given moment, etc. etc. There are quite a few settings actually. And the final one, the reward system. How are we going to give positive or negative feedback? So those 4 are very important, and we will have to go through them one by one for our little Tankdrick case here. The first one is input. So remember the premises here, we are really enthusiastic, but really naive and optimistic. So what would you take as input? I think the only possible correct answer there is, I'll have whatever DeepMind is having. And that is visual observations, of course. Just like the awesome AlphaStar. So why would we settle for less, right? If Google DeepMind can do it, surely we can. I mean, what does Google have that we don't? Apart from, money, computing power, people that can multifold space with just their brain and a sketchbook. I mean, come on, really, what do they have? We have ML Agents, which is partially a product of DeepMind's work. But hey, let's just have a look at it, alright? So, you can pick from 3 input types. First one being visual observation, so the cool stuff that we are going to do. The second is raycasts. Those are basically lines that fire in different directions and then report back when they hit something. And the third one is vector inputs. That's just arrays with data we have to define ourselves. It's the least sexy method, but it's the most controllable and probably the most efficient. You can also combine the 3, but look, we are the cool kids on the block, and in visual observations we trust. So let's just go with only visual observations. We have a GPU all hooked up with our TensorFlow to do that training, so nothing is stopping us, right? The light tank has a detection range of 150 unity meters in all directions, and a unity meter is really just like a regular meter. And for those amongst you still using the imperial measuring system, just stop it. I mean, seriously, stop it. It's a silly thing, it crashes spaceships. I think we can let it go. If we want to give Tankdrick approximately the same vision as the heuristic tank, we will need to give him a 300 by 300 orthographic camera. Now, orthographic is just like your regular camera, except everything is flat. It removes the 3rd dimension. We don't really need 3 dimensions, it only complicates things. A top-down view from a 2D camera should capture enough to distinguish the different game objects, so that's fine. This camera can just about fit a circle with a 150 meter radius, so the Tankdrick will have a slightly larger vision than the heuristic light tank. That's because of the square corners, but that's close enough. Problem I already see though is the size of the image. For ML Agents, I haven't come across an example with a higher camera resolution than 64 by 64, and for our case, I think that's really too low. So this is what that would look like. I don't see how this is going to distinguish between the units. Maybe it's actually possible, but if it is, we're keeping that for a later experiment. For now, let's go with the 1 pixel per unity meter. Pretty sure that's a really bad idea, because this creates a gargantuan input layer, and the algorithm will need to learn what each combination of pixels means. But remember, we are optimistic. So, onward to the output layer. We're not going to be really demanding here. All we want is the brain to choose whether Tengdrik needs to move or attack. And in case he needs to move, he needs to pick a wind direction. You don't even need an accurate coordinate, just a general direction is fine. And if it wants to attack, it needs to pick a target. So our fantastic output layer then looks like this. There's a boolean, 1 is attack, 0 is don't attack, and don't attack can then be move. But for this we have to look at the movement factors. The first one being the forward-backward factor. 1 is forward, 0 is stay put, -1 is go backwards. And the second one is the right to left move vector. 1 is turn right, 0 is don't go anywhere, and -1 is go left. Finally, it then needs to choose what to attack, and here we have 28 options, because there are 28 types of objects. Now honestly, this is probably bad, because this includes options he can never choose. So for example, it includes these resource patches over here. They cannot actually be targeted, but they are in the list of pooled objects. I'm not going to explain exactly what object pooling is, because it's not that relevant at this point. Just know that all objects that can be targeted are in this list. But there are also things in there that cannot be targeted. So for example, there are these 3 units we excluded. They are still in this list, but they're not in this version of the game. So I can already hear you asking, "But Arno, why would you do such blasphemy?" Yeah, the premises was optimism, and I already had this list ready to go without any additional coding, so it's also laziness. Argument made, moving on. If you want an example of this, so let's say 00010 would be to move but actually stay put. The 10 is ignored, and that's a bit annoying here because it thinks it has this option, but it really doesn't. If however it decides to attack, so 1 on the first output, then this renders the movement factors useless. So essentially there is always useless info in the output. And that's because we wanted to do mutually exclusive things, either attack or move, and both attack and move require extra information, either a direction or a target. I don't seem to be able to model the hierarchical nature of the output in a single model, probably because it's not supported by ML agents, because I found a GitHub repository that does exactly this. Maybe using 3 models would solve it, but for now let's just stick to a single one. It's already complicated enough, I think. What we are going to do, however, is action masking. Now, action masking is making some output choices unavailable. We can only do this based on the input though, so we can't say you picked attack, so now we can mask our movement factors. No, this model is outputting everything at once, so that's one thing we can't do. What we can do, and we will do, is mask all the attack options he can't actually attack. Our RTS game already has a system of detection. All the heuristic units are using it, and so we can use it to filter out machine learning outputs. Everything non-attackable, like the resources, suddenly disappear from the output options. That still doesn't leave us with the greatest of output models ever to have surfaced on this planet, I know, but this will already improve learning by quite a bit, so we'll just go with that. That's it for output. Now let's talk about the model itself, the machine learning model we're creating. Or well, let's not talk too much about it, because actually ML Agents has default parameters, and since we're optimistic, we're just going with those. ML Agents comes with very sensible defaults. Okay, that doesn't make it a one-size-fits-all solution, so we are still going to regret this. But we are not changing anything in this file, except for the name, Tengdrik. Do note this part though. We end up with a huge input layer. It's essentially 300 by 300 for the number of pixels times 3 for the colors, because we are going full RGB on this bad boy. The output layer we just discussed. And then we see in the settings file, it will be 2 layers in between the input and the output, each having 128 nodes. And each of these nodes can then take a value. To put it simply, there is not a lot of space to fold a huge amount of input into relatively little output. I think you can already feel this might get a little problematic. But yeah, okay, time for the 4th big element. Last but not least, the reward for our model. In the previous video, I already mentioned the net economic damage dealt, so just a quick reminder, it sounds heavy, but it just means how much damage did you cause to the enemy valued in money after deducting your own sustained damage. So here is the same beautiful drawing you already saw in the last video. If you lose one tank valued at 1000 credits, but you destroy 2, 1000 each, the net value here is 2000 minus 1000, so that leaves us with 1000. Our reward function is going to be exactly this. Except I want to reward Tankdrick not just after it totally destroyed something, I can actually already reward him for any damage he does. It's basically the exact same calculation, except I have to take a percentage. A full unit would be 100%, and if a shot from the tank destroys half the unit, that's 50% of the total reward. And the same time goes for getting hit, so if you get hit for 10% of your health, you lose 10% of the value of a Tankdrick. Also, I don't want a lazy Tankdrick that just hides in a corner, so I'm giving a punishment for just being. I'm giving that every 30 seconds. Now this might sound cruel, but this is actually just exactly how nature works. If you don't eat, you starve, so laziness gets punished. Time punishes you for doing nothing. Now, there's another tricky thing that's pretty typical for neural networks. Neural networks do like their rewards to be between -1 and 1. If it goes outside of these boundaries, the neural network can have a problem converting to a solution, so I do have to normalize these numbers. So they will be then between -1 and 1. Alright, we are ready for this. Let's run that grand simulation of awesomeness. And we are back. We are going to have a look at how great the training went. But before we do, there's a nice occurrence I would like to share. At about 3 hours into the training, the Tankdrick decided to hug enemies instead of attacking them. For a moment there, I thought I found the equation for world peace. I mean, look at them cuddle. Also, they completely ignored the fact that they were getting negative reward for this. So yeah, send that Nobel Peace Prize my way, I thought. I just invented a peaceful AI. It just hugs everything, even while being tempted by rewards for waging war. Good, great. But yeah, okay, so then I started using my brain and suspected a bug. Sadly, I was right, it was a bug. Apparently the rare sort that only pops up after hours and hours of running the same thing. So lessons learned, applying machine learning forces you to run the game for long stretches of time, revealing otherwise hidden bugs. It's a good thing to know, just too bad I'm not getting that Nobel Peace Prize. Yeah, well, better luck next time. Now back to the real deal. For this we have several things to look at. The first one being the tensor board. This here is the cumulative reward function. When a brain starts learning, you expect this one to go up, and after a while, when he learned all he can, this curve will plateau. In our specific case, everything above 0 means Tankdrick has been destroying more enemies than getting destroyed. Below 0, he was totally on the losing side. What we see here, however, is a lot of fluctuation, and also much time spent below 0. Now it's not impossible, the model just didn't have enough time, but it's not really likely. Now you could argue that maybe Tankdrick is just a bad unit then, and maybe that's why it has a hard time keeping the reward above 0. Or like Simon Sinek would say, you know, it's not Tankdrick's fault. He was dealt a bad hand, by no fault of his own. Yeah, okay, so there's a point to be made for that, but it's not true either. If anything, the light tank is even a little bit overpowered in this setting. Remember, we removed the aircrafts, his biggest counter. Also, that was what the entire second video was about, in case you were still doubting its usefulness. And there you could clearly see that there are only 2 units Tankdrick would really need to avoid. Everything else is actually fair game. So was Tankdrick dealt a bad hand? The answer is no, certainly not. So what is it then? I think it's pretty clear at this point, it's just a terrible model actually. And now we're going to watch it in action. I must say, he spends a lot of his time dancing while his friends are going off to war. Maybe it's not too late to collect that Nobel Peace Prize. Or probably he's just guarding those strategically important sand grains over there. Yeah, he's actually brilliant, it's just that we do not understand because we are not smart enough. After a while of tactical circling, he does actually encounter a few enemies. And then he goes for the strongest one. Yeah, sure, why not? Sacrifice for the greater good. Yeah, rush in, make sure you become everyone's target. His bravery is actually quite commendable. His stupidity as well though. I was really aiming for a smart tank here, not a brave dancing one that would fit in the next Step Up movie. So yeah, mission failed I guess. That was really unpredictable though. I had such high hopes after seeing that cumulative reward curve. Okay everyone, that was it for this video. Next video we are going to put a little bit more thought into the entire setup, a little bit less optimistic, a little bit more realistic. So exciting stuff ahead for the next video, see you there.